Hello everyone. First question is define critical path and shortest path. Critical path is the path which creates longest delay in the circuit, and shortest path is the path which creates smallest delay in the circuit. So in this circuit, this is the critical path because this creates the longest delay, and this is the shortest path because this is creating smallest delay in the circuit. Okay, and this path could be from flip-flop to flip-flop. It could be between flip-flop to flip-flop, or between input pad to output pad, or any flip-flop to output pad, or input pad to flip-flop. The next one is what is glue logic. Glue logic is a concept, and what it means is if two modules are connected with some interface, then that is called glue logic. See here, this is module 1 and this is module 2, and these two modules are interconnected by a AND gate. So now this will be called glue logic. And the point that you have to remember is there should not be glue logic at the top level. This one you have to remember. Okay, so this is another example. This is one module, this is one module, and they are connected with each other by this glue logic, and this also includes the combinational logic. Okay, the next one is what is FSM and when it is used. FSM is finite state machine, and FSM are nothing but a sequential circuit used in the digital system or digital circuit design. And what it does, it controls the behavior of the systems. It controls your FSM, finite state machine, controls the behavior of the system and the data flow paths. Data flow paths means how the data is transferred from one place to, or one point to another point in the circuit. Okay, and in the digital logic design, the FSM are normally used to design a controller. For example, in a vending machine controller, traffic controller, or your controller for a processor. So finite state machine is normally used to design a controller, and it is a sequential circuit used in digital system. The next one is what is setup time and what is hold time, and what is setup time violation, what is hold time violation, and what is metal stability in logic design. Setup time is, it is a minimum time for which data should be valid or stable at the input edge of clock. Meaning, see, this is my clock signal and this is my data. So the data should be stable. Stable means here, if it is 1, then it remains 1, and if it is 0, it remains 0 for some amount of time. Here this is positive edge of clock, and before positive edge of clock the data is, here the data is 1. Okay, so it is constant for some time. So this time is called setup time. So data should be valid for the amount, the time limit given by the next one is what is setup time, what is hold time, what is setup time violation, what is hold time violation, and what is metal stability in logic design. Setup time is the minimum time for which data should be valid or stable at the input before edge of clock or positive edge of clock. And hold time is the minimum time for which data should be valid or stable at the input after edge of clock. Meaning, this is my clock signal and this is my data signal. So first it was 0, then now it changed to 1. See here, so before this positive edge the data remains 1 here. So it is stable now. Here stable means valid, or stable means if it is 1 then it remains 1, if it is 0 then it remains 0. Okay, so here it remains 1 for some time. This time is called setup time. See here, it is the minimum time for which data should be valid or stable, means if it is 1 then it remains 1, if it is 0 then it remains 0 at the input before edge of clock. This is called setup time. And what is hold time? After the positive edge of clock. So this is after edge of clock. Here the data should be valid or the data should be stable, means if it is 1 it should remain 1, if it is 0 it remains 0. So here, see here, after edge of clock it remains 1 for some time. This minimum time is called hold time. Okay, the setup time is the minimum time for which data should be valid before edge of clock comes, and hold time is the minimum time for which data should be valid after this positive edge of clock comes. Okay, and if there is a violation in this setup time or this hold time, that is called setup time violation. And if there is a violation, that means if data is not stable during this period, during this whole time period, then it is called hold time violation. Meaning here, for example, here, see here, in this case, if it is, this is data. Okay, so here before positive edge of clock the data is changing. First it was 0, now it is 1, then it is 0. So it is continuously changing to from 0 to 1, then 1 to 0, and it is not constant, it is not valid, it is not stable. So this case arises if data is changing again and again before this positive edge of clock, then it is called setup time violation. And if data is changing after the positive edge of clock for some time, here it is, see here, it is 0, then 1, then 0. So it is not constant, it is not 1 or it is not 0, it is changing from 1 to 0 or 0 to 1. So this is called hold time violation. And this setup time violation and hold time violation causes metastability. So metastability is nothing but a setup time violation, and the hold time violation is called metastability in logic design. Metastability means the data is neither 1 neither 0. Okay, so your system is not going to read, whether it not going to analyze, or it will not get to know whether the data is 1 or whether data is 0. Okay, so this condition is called metastability, and which is because of this setup time violation and hold time violation. Okay, next one is what is race around condition in Verilog design and what is its solution. Race around condition is one signal, if one signal is driven by two always block. Same signal is driven by two always block. Here see, this is one block, and here one signal is out. Okay, here another always block. Here same signal, we are using the same signal, out, both are same, right? So here in this condition, here out is evaluated in two always block and creates hardware conflict, and this is called race around condition, because whether this output will be considered or whether this output will be considered is not decided by the simulator, we can say simulator or your synthesizer, and it creates hardware conflict, and this condition is called your race around condition in Verilog. So one signal cannot be driven by two always block, and if we write same signal, or if you are driving same signal in two always block, then it will show you an error, and that is called multi-driver error, and this type of condition is not synthesizable in Verilog. Okay, and what is the solution for this one? The solution is using zero delay control, which I have already discussed in one of my Verilog interview question and answer series in the tutorial. Okay, so that is using zero delay, that means hash zero you have to use to find the solution for this one, or to eliminate this race around condition. Okay, next one is what is zero delay. Sorry, this one only, already I had explained this one. So zero delay in already explained. Okay, zero delay in Verilog. So this is nothing but using hash 0. If we write hash 0, then the system will get to know that this procedural block will be evaluated at the end after the first initial block. Okay, the next one is what is one hot encoding technique and its advantage. This one, see, I have uploaded one tutorial in my YouTube channel, that is FSM part 2, and there I have explained this one, this hot encoding technique. What is hot encoding technique and what are the advantages using this hot encoding technique. So please go and watch the tutorial if you have not watched till now. The next one is what are the latches in Verilog coding. Next one is what is unwanted latch. Unwanted latch in Verilog design, it results from incomplete case statement or conditional branch. Means if you mention if, but if you forget else, if then statement but else, there is no else part. If you forget to write else part, so that will generate unwanted latch. Incomplete case means, see here, the select and select bit is 2 digit, right? That means 2 bit signal. So the select and select B could be 0 0, 0 1, 1 0 and 1 1. But here the conditions are 1 0 and 0 1. But here what is missing here is 0 0 and 1 1. So let's say after when 0 0 comes, what is unwanted latches in Verilog? This unwanted latches in Verilog results from incomplete case. Incomplete case means, see here, case select A select B. The select A select B could be 0 0, 0 1, 1 0 and 1 1. But here only 2 conditions are there, 1 0 and 0 1. What is missing here is 0 0 and 1 1. So if 1 0 comes, then out equal to data A. If 0 1 comes, then out equal to data B. So if 0 0 comes and if 1 1 comes, then the out will remain this one, the previous data. It will remain data B, and in this case also 1 also out equal to data B. So what it is doing here is it is saving, it is storing the previous data, right? And storing previous data, this is a combinational circuit, but it is storing something. And storing something means definitely it is generating a hardware that is not combinational, but that is sequential. Because only sequential circuit can memorize data, the previous data. It can memorize previous data. So here what it is generating, this hardware will generate, because here these 2 conditions are missing, so incomplete case, so it will generate a sequential circuit, that is a latch. Okay, like this, if conditions are incomplete, for example, if is there but else is missing, then it will generate incomplete case. For example, if A equal to 0, Y equal to 5, and there is no else condition. Okay, so what it will do, if A equal to 1 comes, then it will, the Y becomes 5 only, what it was before during A equal to 0 condition. So it is storing previous value, right? Previous value means definitely it is a memory element, there is memory element. So this condition is called unwanted latches in Verilog because of incomplete case and incomplete conditional branch. Okay, the next one is difference between RAM and FIFO. RAM is random access memory, FIFO is first in first out. Okay, FIFO doesn't have any address line, but RAM has address line. RAM is used for storage purpose, storing data. FIFO is generally used for synchronization purpose. Okay, and FIFO is used for CDC. CDC mean clock domain crossing. Okay, what is gated clock? Gated clock is if clock comes from a gate, generic gate. Okay, this is called gated clock, because now clock is not direct. See, this is the source, this is the clock source. Okay, this is the clock source. Clock is coming from here, and this first flip-flop, it got the clock, direct clock from here. But here this second flip-flop, it got this clock or received the clock through this AND gate. So now this clock signal is being controlled by this AND gate, and because of that one, the this flip flop may clock at wrong time. Okay, and this may leads to glitches in your circuit, and this is what is called gated clock. If clock is being controlled by a gate, okay, and this could lead to a glitch, or meaning the flip flop may clock at wrong time. Okay, next is what is false path. False path is the paths in the circuit which are never exercised or never executed during normal operation for any set of inputs. Say, if a condition never occurs, means never be executed, that means it is dead completely. So we have to remove such part or such code, and this false path is identified during the STA, or that static timing analysis, and identified by STA tools. If we remove false path, then it makes the circuit testable and make the timing performance predictable. See here, example is, this is my circuit and this is the code. If C equal to 1, or if C is true, then output equal to A plus B, this one, else output equal to A minus B, right? So here C equal to 1 always, right? This is my select signal, so here C equal to 1 always. C never becomes 0 here. That means if C equal to 1 always, so this line will be executed all the time. Output equal to A plus B, and it is never going to execute this part, else output equal to A minus B, because C equal to 1 constant. So this line never gets executed. That means this path is never get executed, this path. So this path is called false path. The path in the circuit which are never get executed during normal operation for any set of inputs, that path is called false path. So in this circuit, this is my false path, because this condition, that is C equal to 0 and A minus B, this path is never get executed. This is called false path. Okay, next one is what is SOC. SOC is system on chip, and I have uploaded one complete tutorial on this topic, that is system on chip. So please go and watch my IP tutorial, intellectual property tutorial. It is there in the YouTube channel, in my YouTube channel. The next one is what is CDC. CDC is called clock domain crossing. In VLSI design, CDC refers to the process of transferring a signal or data between circuits operating under different clock frequencies or sources. So CDC is clock domain crossing. It is a process of transferring data between two circuits operating at different frequency. So this is clock 1 and this is clock 2. Let's say it is 50 megahertz and let's say it is 100 megahertz. And if you want to transfer data between these two module or two circuit, then there should be some kind of synchronization, right? Because it is 50 it is very slow, this is, and this is very fast, so there will be a mismatch of data. This process is called clock domain crossing, because here clock is crossing from one domain to another domain having different frequency, and this concept is called clock domain crossing. And so in this case there is a concept called synchronization between this two clock, or between the data that is being transferred from one domain to another domain having different clock. Okay. Next, the next one is, what is LUT in FPGA? LUT is called lookup table. Okay. And FPGA implement combinational logic with the help of LUT. So when we write any combinational logic and try to dump that code into FPGA, let's say AND gate. You want to implement AND gate, write a code of AND gate and want to dump that code into FPGA, then how this FPGA is going to react, how the FPGA will get to know what the output should be. Okay, so inside FPGA there are lookup tables, so many lookup tables are there, okay, inside FPGA. So when we write or when we try to implement this 2 input AND gate, then see, this is the truth table 0 0, but 0 0 0 0 1 0 1 0 0 and 1 1 1. So inside the LUT for AND gate, inside the LUT, what is stored is this one, this output. If it is OR gate, then there is a lookup table for OR gate. And what is stored inside this lookup table is 0 0 gives 0, then 0 1 1 1 0 1 1 1 1. So here it is 0 1 1 and 1. So this is for OR, to implement OR gate. This is to implement AND gate. Okay. Then based on the input, whether it is 0 0 0 1 1 0 and 1 1, you get the output. So LUT is basically a table that is inside FPGA to implement combinational logic. Okay. Lookup table consists of block SRAM. So this is a memory, okay, that is indexed by the lookup table's input. So this is the input. The output of the LUT is whatever value is in the indexed location in its SRAM. So this is lookup table, and this lookup table is nothing but the SRAM, and based on the input, we are extracting data from this SRAM, which is here is lookup table, and you are getting the output. Okay. The next one is, what is the use of parameter in Verilog? Parameter is in Verilog is a construct which is used for reuse purpose. To reuse something, we use parameter in Verilog, and it is basically a constant. That one you have to remember. Okay. So here, if we write parameter MSB equal to 7, means MSB is a parameter with a constant value 7. Parameter real equal to 4.5 means this real holds a real number, this one. Then parameter FIFO depth 256, maximum width 32. So we are declaring here two parameters. Parameter 7 is to 0, F constant 2b3. So this is a 2-bit value. 2-bit value is converted to 8 bits. So it is 2-bit value. Then we are converting this one to 8 bit. So here it is 7 is to 0. Okay. If you write here parameter n equal to 2 and here parameter down equal to 0, so this is a 2-bit up counter. Okay. See here, tomorrow you want to change this code to 3-bit up counter or 4-bit or 5-bit, then what you are going to do? Again you have to write the whole code, right? For 3-bit. If it is for 4-bit, then again you have to write. If it is 5-bit, then again you have to write. No need to write this code again and again if you want to change this one 2-bit to 3-bit to then 4-bit then 5-bit off counter. So here parameter is very useful concept here, construct in Verilog. So it is, we are using parameter for reuse purpose. So here you write like this, parameter n equal to 2, parameter down equal to 0. Tomorrow if you want to change this one to 3-bit counter, then what you have to do? You just change this one, this n equal to 2, instead n equal to 2, you change this one to 3. And this one will become n minus 1 means 2 is to 0, that means 3 bit. Tomorrow if you want to change this one to 4 bit counter, then you change this one to 4 and it will be 3 is to 0, that means 4 bit now. So you will be able to count 0 to 15. So this is how parameter is used. If you want to modify, means there is a flexibility in the code, right, if we use parameter. The next one is time scale in Verilog. What is time scale in Verilog? Time scale specifies the time unit and the time precision of a module that follow it. This is the format: time scale, then unit, then slash, then precision. This is the example. Time scale, the time unit is 1 nanosecond and the precision one is 1 picosecond. Okay, the first one is time unit, the second one is precision unit. Okay, and while writing Verilog, if you are not writing this one time scale, then by default the time unit and precision are 1 nanosecond. Okay, and this time scale unit, this construct has no effect in synthesis, means your synthesizer simply ignores this line. Okay, and see, if you write like this, hash 5a equal to b, meaning a is updated 5 nanosecond later, because default one is nanosecond. So this is 5 means 5 nanosecond. But what is this precision is? Precision means here is, if you have written this line 1 nanosecond by 1 picosecond in your Verilog code, time scale 1 nanosecond, slash 1 picosecond, and if you write this line hash 8a equal to b, meaning calculator will check the time unit is in decimal or fraction or without fraction. If it is without fraction, then this will be considered in nanosecond, this one 1 nanosecond, that means it will be 8 nanosecond. And if this line is there, if you have written this line in Verilog, this time is in fraction, right? So fraction means this will be considered in picosecond. So here this one will be converted into 8280, that means this 8.284 will be rounded off to the nearest picosecond. So 8.284 will be 8280 picosecond, and the simulator will give you only integer value. Simulator doesn't understand anything about the second, nanosecond. It only unitless integer will be considered by the simulator. Okay, so this is what is time scale in Verilog. So what are the design constant in any VLSI design? The first one is time, then area, next one is power. Okay, this type of question also in Verilog interview many more times they have asked. And so the first one is BJT versus FET. You know this one, BJT is bipolar junction BJT is bipolar junction transistor, JFET is junction effect transistor, then one is controlled, current control, another is voltage controlled. Then what is RAM and BRAM? RAM is random access memory and BRAM is block RAM. Block RAM, this BRAM is used in FPGA to store data. Okay, sensitivity list and its importance means if you do not mention, then what will happen? For example, always block, and if you do not mention any signal here inside this parenthesis, then what is going to happen? If no sensitivity list, then always block runs continuously for infinite time period. Your always block will run if there is no sensitivity list. Presence of sensitivity list means whenever any signal in sensitivity list changes, then the always block is triggered, or the always block, whatever is written in this always block, is activated. Okay, so today I am stopping here, and thank you so much for watching this tutorial.